Version 2, question 3. We are told on our data sheet that Elsa models the value of the fraction of the moon, and we know that she uses a trig equation. So, important bits on this. We've got T as the number of days after the 1st of June, and F is the fraction of the moon visible. So, on what day would she expect it to be in the 3rd quarter? The 3rd quarter is going to be 0.75 or 3/4. So for part A, we know that the fraction that we're interested in is equal to 0.75. So we can substitute that into our equation. We need to show that we've substituted it. 12t plus 6 plus 1 all over t. So, from a calculator point of view, if we go into graphs and we get rid of all of the stuff that's currently in there, okay, so we've got a fraction, so we need 12. Our calculator doesn't give us a t, so we just need to call it x, and that's over 2. And then if we draw it, we need to make sure that you've got a view window that's sensible. So if we've got a view window that goes up to 1.5, nope, in the x direction, we need the whole month. And if we stick that in there, and that can go up to 2, so we can make sure we can see everything. So if we've got f, then we need to calculate x, so we can do gsolve xcal, y value is 0.75, and we've got t equals 2, and we also have equals 12, and the next one after that isn't in June. So, given that we know it's the number of days after the 1st of June, when t is 2, that is the 3rd of June, and 12 days after the 1st of June is the 13th of June. Okay, how much is the moon illuminated on the 10th of June? So we need to make sure that we know what our value of t is. So for part B, on the 10th of June, that is going to be when t equals 9, because it's 9 days after the 1st of June. So if we substitute that into our equation, we've got sine brackets 12, put the 9 in where the t was, still divided by 2. So we need to make sure that we've shown that we know what we're doing and we've substituted it. So we need to calculate the thing that is our y value. So if we do gsolve ycal when x equals 9, that gives us a value of 0.957 to 3 significant figures. Okay, part C, a new moon. A new moon is when there is no moon visible in the sky. So the fraction at that point that you can see will be 0. So shuffle that across a bit, and that'll fit in there. Okay, so for your new moon, your fraction is 0. So if we substitute that into our equation, we have sine 12t plus 6 plus 1 all over 2. T is 22, so that will be the 23rd of June. Okay, question D, the period of the lunar cycle. This bit's important that your calculator is in degrees rather than radians. Radians is for the A2, but you need it in degrees for the AS. So the period is going to be 360 divided by the frequency, which is 12. So 360 divided by 12, and that gives us 30 days. Okay, in reality, a lunar period is 29.5 days. So if they're asking you for a period, you ought to be expecting something around 29.5 on this sort of question. Okay. E, crime rates increase when the moon has less than 40% illuminated. So less than 40% illuminated is when your fraction is less than 0.4. So on a calculator, we've got GSolve xcal 0.4. So that starts here, and it's going to be less than right the way along to the next point. So that is going to start at 15.5, and T is going to go up to 28.5. So if we know this bit, what we can do is we can put that across into dates. So that will be the 16th to the 29th of June. Okay, so F. F is filling in the table that we've got here. What's useful is if you come out of this one and go into your table and set up your table going from 0 to 30 in steps of 5, it will then give you the values that you need to be able to plot. So there is also something else that's slightly sneaky on this calculator that's been set up, but I'll explain that in a second. So 957 0.905 0.448 0.043 to 0.0954 and 0.005. 0.552. Okay, the other points that will be needed to be plotted are a maximum point and a minimum point, and ideally when it goes through the midpoint. This calculator is currently set up to show you the differential, so the gradient at any point. So if we're looking at the gradient when t is 7, actually what we can do is plot that in, and it gives us a gradient of 0, which tells us that that is going to be our maximum point. Okay, so if we come out of that for a second, go back into our graph, points that are going to be important, we need to plot the maximum point, and that is x is 7, y is 1. So if we go 0, 5, 10, 15, 20, 25, 30, that'll be 1. So first off we need to plot 7 and 1. If we make sure our minimum's in the right place, that is going to be at 22. So that's going to be there. And it's worth just checking the x values when y is 0.5. So we've got 14.5, so that's at 0.1, 0.2, 0.4, 0.5. Okay, so that's 14.5. And the next one is at 29.5. Okay, so those are going to be the key ones that need to be in the right place, as well as the points that we've actually been asked to plot. So first off, we've got our first one, that's coming in here. We've then got 5 and 0.95. We've got 10, which is there. We've got 15, which is there. We've got 20, that is 0.04, which is there. 0.09, which is there, and then 30 is at 0.52, so about there. Key things that they are looking for when you are doing graph sketching. You need a smooth curve. They also talk about a sawtooth. A sawtooth is like it looks like on a saw, which goes straight up and down. You're not allowed that either. So it's going to be flat at the top. You may well find, just because of biology and the fact that wrists move that way, if you turn your piece of paper, you stand a better chance of getting a smooth curve than, unless it goes over another bit of paper, you stand a better chance of getting a smooth curve than you will if you try and do it the other way up. Okay, so one approximately smooth curve. And it asks about the gradient when t is 7, and that happens to be our maximum point. So you end up with a gradient that goes flat along the top. So you've got gradient of 0 at that point. There we go. So gradient equals 0 because it's the maximum point. Okay, lastly, we are asked for the transformations. You need to be a little bit careful here because often the equations that they've got here aren't quite the same as the ones they've got here. So for example, this one has lost the plus t just so that it makes it a little bit easier. So, what we've got here, this equation, if you take it out of this form slightly, what you'd have ended up with is a half sine 12t plus a half. And this bit may make it slightly easier to work with because what you're effectively looking at is that bit there, which is a stretch in your y direction, so parallel with the y-axis, of a half, and then you've got this bit here, which isn't in the brackets with the x, so is also happening to the y, and that is a translation of 0 a half. Yeah, that'll do just about. Okay, on our second one, if we look at the differences, we've got this one, which is plus 1. So you've got a translation of nothing in your x-axis and 1 in your y. And then the other bit that you've got on this one is this 12. It's happening in the x-axis. So whatever it is, it will be the reverse. So you're looking at dividing by 12 rather than a scale factor of times by 12. So we write that as 1 over 12 in your x-axis.